So let's speak about this partition function, and let's do it by running some code. I'm going to need a function to swap the elements in two positions on my list. So I have this one. Give it my list and the two positions, and I swap the two elements. For those of you following all the courses, notice that this is using tuples and tuple unpacking. And now I'm going to define my partition function. Okay. The first thing that I will need to do is choose a pivot. Okay, and let's just run this in this part, the partition function, which receives a list and two indices between which I want to sort my list. In this case, there are many strategies to do this, and here I'm going to be using the random position of the pivot because it works pretty decently. I will say a little bit more about this later. So the first thing I'm going to do is choose a position for the pivot and put my pivot in the first position in my list. Okay, so I swap the element in position pos for the element in position first and make a note of my pivot value. What do I want to do with my partition function? Remember, I want to end up with the pivot element in the correct position, smaller elements than it before, and bigger or equal elements than it after the pivot. So I'm going to have two markers. I'm going to have a marker called left that marks the position that are the last position, the position after all the elements in the list that are smaller than the pivot, and I'm going to have the right marker to signal the position before the last element known to be larger than the pivot. So I'm going to have these two markers, these two flags that are going to grow and are going to help me set up this partition. I'm going to start by putting left at the first +1 element in the list, so just after the place where I just put the pivot. Okay, I put the pivot in the first one, so let's put the left marker that indicates the smaller elements just after that one, and let's put the right marker at the end. So where is it? Here, at the last element. So let's set these markers in the most extreme positions, and let's move them. As long as what I'm pointing at with left is smaller than the pivot, I can move, because that's fine. And as long as what I'm pointing at with right is bigger than the pivot, that's also fine. And if that stops being true, then I will have to do something else. Okay, so here I'm advancing left while it's not reached right and it's smaller than the pivot, and I'm decreasing right while it's not at the end and it's smaller and its value is bigger than the pivot. Okay. Once I have stopped, either because left and right have met or because someone is not where it should be, either the element pointed by left is bigger than the pivot or the element pointed by right is smaller than the pivot, then if I have not finished, if right and left have not met, then I swap the elements in pointed by left and right. Someone was wrong there, so I'm going to swap them and I'm going to be able to keep iterating. Okay, let's run this code. Finally, once I have finished doing that, I'm going to put the pivot in the correct position. I had it in the first element, but I don't want to have it in the first element. I want to have it exactly where right and left end when they meet. Okay, that point is where the last element that's smaller than the pivot is and the first element that's bigger than the pivot is. So I'm going to swap the one that's smaller than the pivot for the first element. Okay, I'm going to put the pivot in that boundary position, and the last element that was smaller than the pivot, I'm going to put it in the first position. So am I breaking the order here somehow? No, because all the elements that are smaller than pivot are before the pivot, and they are not sorted between them. They are all smaller, they are not sorted, okay? So with this, I achieve my goal of having all the elements that are smaller than the pivot before it and bigger than the pivot after it. Let's run this. And here I have added some, how would we call them? Some print statements here that tell me what's going on with my code. I've even added a Boolean value verbose here so that I can turn them on or off easily, okay? And what I have done here is that I have defined a list so that I will always have the same result, and I'm partitioning it because there is a random component. Every time I change my list, I have a different output. Okay, let's check this one. For example, I'm going to start partitioning my list with first 0 and last 13, which is the last one, and I'm going to randomly choose a pivot, and in this case, in this execution, I got pivot 3. The list after swapping 3 for the first position is this one. Okay, so this guy came here. Left is now 1 because I said I would initialize left after the pivot, and right is now 13, so the last element in the list. And now I have the list, and I'm going to move left and right because 10 is larger than the pivot. Right decreases. Okay, so this is okay. I'm going to decrease this. Then left hasn't moved because this should be smaller than the pivot, and it's not. This has moved 1 because this should be bigger than the pivot, and it is. So now I have to swap these two guys. Okay, and I do, and I get -3 here and 6 here. Now left can advance a couple of steps, and right stays. Right can decrease 1, 2, 3 steps, and then I swap these two guys, and so on and so forth. After the partition, I end up with 3 in its correct position, all the elements that are bigger than 3 after it, and all the elements that are smaller than 3 before it. Okay, you can have a look. This is an example of how to use these print statements to follow the trace of execution of the algorithm to see how it's working. You can do it to explain how an algorithm works, and most of the time we do that to find an error, because when you code algorithms, you get errors always. Okay, so I have given some details, and I encourage you to come here and play around with this code a little bit more until you feel confident that you understand how partition works. But with that partition that now works, now I have a proper functioning version of Quicksort. Okay, I have the same code that I had before, but I have added a couple of statements with this verbose function to make the output a little bit prettier. And you can see here, for example, that I start with an unsorted list and end up with the same elements on the list, but sorted. From now on, we will be speaking a little bit about the complexity of Quicksort, which is a bit tricky. We will see some runtimes, and we will also introduce some small improvements to Quicksort and locate it in the, let's say, wider world of sorting algorithms, including Python's sort, which is an algorithm which uses an algorithm called P2Sort. Finally, we will use all of that and all of that we have seen so far to speak about algorithm complexity for the, sorry, not algorithm complexity, problem complexity for the sorting problem.